Okay, thanks for joining us. November, I know it's a holiday week, but we really appreciate you being here. And today, of course, as you know, we're going to be talking about some of the tools and databases and models that we have available for current use. Also, for those who may be new to the webinar, you can receive a certificate for continuing education contact hour. For this, let me actually, okay. And to receive this certificate, we do post the recordings of these webinars, but you do have to attend the live webinar to receive that certificate. And we do like you to try to be on for the full 60 minutes. If there are people in the room with you who would like a certificate and aren't logged in, if you could just provide those names in the questions box. There's a question box on your navigation bar, and you could actually type names in there, or you could, on the first slide, which you will receive in an email later this week, there is a contact information for submitting names for that certificate. Okay, today we have two speakers. You may recognize the first speaker, Dr. Thomas Speth. He actually usually moderates this webinar. Some of you may also know him from professional experience and also at our drinking water workshops that we have every year. Tom has been with the Office of Research and Development for 29 years, but he is currently on detail with EPA's Office of Groundwater and Drinking Water as a senior engineering advisor. So he will be presenting for the Office of Water today. And then we have Dr. David Wamman, who will be presenting for Office of Research and Development on a new tool that he has developed. Okay, before we get started, I want to let everyone know that we will pass out this presentation by the end of the week via email, and we also record this webinar so you can view it later, and the link to that will be on the website, and you will also receive that in an email. And also, at any time, we are going to have a 30-minute optional Q&A session at 3. So at any point during the talks, you can ask a question by entering it in the questions box, and we will actually read those out loud at the end and have a Q&A session for 30 minutes. So with that, I'm going to actually go ahead and turn this over to Dr. Speth to start the presentation.
Okay, thank you very much, Michelle. And I believe my screen should be popping up. I'd like to acknowledge my co-author, Rajiv Kara, also from the Standards and Risk Management Division of the Office of Groundwater Drinking Water. Rajiv was the lead on the EPA's cost models. Unfortunately, he's ill today, but I'll be presenting the talk and moving forward with that. I'd like to also acknowledge Pat Ransom from ABT Associates, who has worked over the last few years on this project quite extensively. So the next slide here is the treatability database. This is a summary slide on that. It's an interactive database that contains over 60 contaminants, both regulated and unregulated. It has 34 treatment processes in that database that are commonly employed or at least known to be effective for more novel technologies. It has thousands of literature sources within the database, all within this one location on EPA's website. Some of the compounds added recently, we want to keep adding compounds and updating compounds. Recently, carbon tetrachloride, nitrate, strontium 1,2,3, TCP, and cis-1,2-dichloroethene have been added to the database. The database has many uses. First of all, identifying effective treatment processes for either a utility or a community or anyone interested in how well a treatment process removes a contaminant. And that might include people like first responders for security and spill events, EPA, federal EPA employees for regulatory review and designating best available technology, and academia for identifying research needs. So a little bit about the cost models that I will be discussing also is that these cost models that Rajiv Kara was the lead on were used by EPA to conduct, can be used by EPA to conduct benefit cost analysis for a new drinking water regulation. Each model estimates the unit cost, both capital and operating, of a specific drinking water process. Now, on mentioning that, so the model was developed for EPA's use in developing regulations. However, within this model, you can also do the costing for an individual treatment system, individual utility startup of a brand new plant. You can also look at add-on technologies to an existing plant, retrofitting a current plant, and even going down to modifying the operation with the treatment plant and then determining the delta cost, or the cost that would be different than if you operated as currently. The treatment technology, a little bit more about the model, is that it's broken into discrete components or breakdown structure that can be measured. So all the specific equipment like tanks, vessels, pipes, and instruments are all costed out, and they are added up. Other identifiable cost estimates like construction, labor, chemicals, energy, O&M type costs are also within this database. So everything is included. So why are we putting these two models together? Well, EPA has a grand vision of merging the treatability database with the cost models. And so we can have a system where the treatment performance feeds directly into the cost models. So we don't have to do as much work. We can use the treatability database as the data input into the cost models, making it a very transparent way of creating a regulation per se, if we get to that. So that everybody can see how it's done, and also so that it makes it a very simplified process so that other people that have a use for estimating costs at a drinking water plant can use it. So here are those benefits: transparency, needing to reduce the effort to get cost data, provides an opportunity to focus on contaminants of interest to small systems, and I'll get into that a little bit of how it can uniquely take into account small systems. And finally, I'll touch in the very end of the talk how we can work with universities both in supplying the data and using the data. So a little bit more specifically, I'll break it up into two parts of this talk. The first will be on the treatability database. So as I mentioned before, it has thousands of sites and it has many uses. The web page link is listed down below on the bottom in blue. I recognize that it's a little difficult to scribble that down. EPA has changed how they do, where the web pages are located, so the addresses are a little more complex. So if you go into a search engine and type in EPA space TDB, it pops up in the top 10. So if you could use Google, Bing, Yahoo, it will if you put in those search words, it will pop up in the top 10. Ironically, if you go to EPA's webpage and search the EPA's webpage for EPA space TDB, it doesn't show up in the top 10. So you may wish to use one of the more commercial search engines. Okay, so what I want to do is, if you can see my screen, I'm going to pop out of my talk and go right to the treatability database live. So this is the database, and I'm assuming that people can see, since this is a webinar, we can see a little bit better of the screen, perhaps at your desk. But if not, if this is on a big screen somewhere, I'll try to talk as broad as possible so you don't have to look at each individual word. But here is the treatability database live. It's broken up into two ways of doing things. You can look at whether it's a contaminant that you're interested in. You can search by that, and then it will identify the treatment processes that we have data for that contaminant. Or you can look at a treatment process and then click on the contaminant for which we have data for that treatment process. In the end, you end up in the same exact pages. So let's just start with find a contaminant. So you can either click up here in the blue, or you can click down here. It takes you to the same place. And here is a list of the 60-some contaminants listed down as I'm scrolling down the screen. And if you choose one of these, let's just pick microsystems, because that's common, these very popular one these days, it'll bring you to a screen that looks like this. So it gives you an overview of microsystems. And then across the top, you can look at treatment processes that there are data for, properties, fate and transport, and all the references that we found for microsystems. So a little bit about the treatment processes tab, because that's what all this database is all about, treatment. It gives an overview of the treatments and a little bit addresses issues, and then listed here are all the different treatment processes that we have data for microsystems. Now, some of these pages are updated a little more recently than others on the treatability database, so I think somewhere we designate the date, but we're trying to keep them all fairly up to date. So if we click on granular activated carbon, for instance, for microsystems, it brings you into a summary sheet. If we go to data, it lists down the data that are in the database that we have information for. This blue bar here has all these specifications, or all the what we could glean out of the paper. So if I scroll over across that blue bar, you'll see things like, percent removals, or GAC manufacturer, GAC product name, a little bit about time and service of the column, the empty bit contact time. In the end, we have comments about the paper, whether or not, what specific issues that we want to call to your attention. So all the data is listed here. The different treatment processes will have different headers across the top, depending on whether or not they're important or not to that technology. So let's go back to microsystems. Again, we can go to treatment processes, and just a little demonstration of that. If we go to conventional treatment and click on data, the descriptor there for conventional treatment will talk about microsystems. If they're intercellular, you can remove them with conventional treatment. If they're dissolved or extracellular, then conventional treatment is largely not effective. So you get that type of description within the summary. And here are the bars for conventional treatment. And obviously, you see things more about coagulation, phosphate addition, turbidity, and columns that you don't see on the GAC page. So a little bit about that. Let's go back to the original find a contaminant sheet. I just wanted to point out within the treatability database, there's listings of microbes and chemical contaminants, both, and radiological contaminants. So we do have microbiological contaminants within the database. If you type in anthrax, you can see the treatment processes for anthrax. And it's much more limited. Of course, we're looking more on disinfectants in this case, and you could go into those. And again, the columns will all change what the technology is. A little bit back, and one last contaminant I'll pick is arsenic. So we can click on the A here. It will take us to all the contaminants that start with A. We can choose with arsenic, and again, those same columns across the way. If we hit properties, we can pull up the properties of the contaminant of interest. Fate and transport is a tab that's not well populated in this database because it's not the intent of the database, but for some contaminants it's very important. And then references. So here are all the references that we found, and this is good for literature searches for a contaminant, and it goes down and down and down because there have been hundreds and hundreds of papers on arsenic. The interesting thing with this database is if you ever want to manipulate the data within it or the references, you can export it to a spreadsheet, and that's where this is where you would click if you want to do that. So instead of doing that, because it takes a while for Excel to load, what I'm going to do is click this button and skip all my screenshots that were on the database, that were my backup slides, and go right to what the spreadsheet would look like. And this is just a standard Excel spreadsheet, and it has all the information from arsenic, I believe, that you would be interested in, and you could manipulate these data if you were interested. So that's a brief rundown of the treatability database. I'd like to then talk a little bit about the work breakdown structure cost models that were developed. in the Office of Groundwater Drinking Water. So these models have a number of different aspects of them which make them very useful. The first is that they're engineering-based designs that have been peer-reviewed, and so all the assumptions into this database are vetted. Secondly, there are flexible inputs that you can easily change for the database, and you can put in different contaminants and different aspects of a contaminant's treatment effectiveness, and it will recalculate the parameters. Also, the unit cost database is a very valuable component to this. So as I mentioned, the work breakdown structure identifies the cost of all pieces of the system. The unit cost database has the cost of all those parts, thousands of parts, all costed out. Now, 80 or 20% of those parts generally account for 80% of the cost of a system. So those 20% of those parts are reviewed every year in the WBS cost models and updated every year. So the costs are up to date. The 80% of the items that account for 20% of their costs are only updated every 3 years, but in the interim years they are adjusted, their price index to account for inflation. So we feel that this database is very much up to date and will remain up to date in the future in terms of being a valuable database to use. Finally, the assumptions within the database, which there are over 100 assumptions within this database for the cost model. Every one of them can be edited within the cost model, and the manual will show what sheet to go to edit those assumptions. And finally, what the model produces is the component level cost output. And so in this next slide, a little bit about how the costs are done. So as I mentioned previously, it will calculate the capital and operating costs, and you can do that for different contaminants, looking at different baseline or compliance conditions. So a little bit of information on what is work breakdown structure. Work breakdown structure, as I mentioned, is it prices out all the specific pieces of a system. So valves, piping, pumps, tanks, instruments, all of those are costed individually. And this is a schematic of a pressure GAC system. So you cost out every individual one, and then you start to sum them up. And that is diagrammed here. So things like process equipment, building, add-ons, indirect costs all feed into the capital costs. Things such as labor, materials, energy, residuals feed into the operating costs, and then those total up into the system costs. So it's very much a bottom-up approach for costing. An example is a GAC system. I think I showed a schematic of that in a prior slide. So if you assume 40,000 bed volumes to break through, for instance, until you get to a point where you have to regenerate or replace the carbon. 10 minutes of empty bed contact time are some very standard inputs, major inputs into the model. And then the cost curve outputs will generate all the capital and O&M costs for a system. I'm not going to get into the Excel spreadsheets of the cost model because they're very detailed and they're really difficult to see. But here is just a shot of the spreadsheet for GAC, for instance. It steps you down what inputs you have to do. And once you put those inputs in, it will calculate an output page for you, and you're off and running. There are numerous other sheets in the spreadsheet down here below with all the design assumptions, O&M assumptions, indirect cost assumptions, contactor constraints, retrofit issues, and the list goes on, where you can go in and modify those sheets if you wish. So that's how that's how the flexibility is brought into the Excel spreadsheet. And all this is an Excel-based spreadsheet. Here is a capital cost curve. As I mentioned, this is used by EPA as a way to set up national regulation, or will be in the future. And so we have to do that for all different size systems. We've broken up into 3 categories: small, medium, and large. And I should mention that typically when you talk about a small system in EPA, it's designated as serving 10,000 people or less. In this case, the model breaks it at 1 million gallons a day, which is more along the lines of 2,700 people or so. And so the actual small system, by definition of the EPA, is somewhere in the middle of this blue area here, is the start of small systems and beyond. But I'll tell you why in a little bit of why we did that. And the main reason is that at 1 million gallons a day, that's where you start to see some flexibility in terms of how you design a system for a small system that you don't have with larger systems. And I'll go over that as we move on. So again, 10,000 people are somewhere in the blue. Some of the microbial rules says it at 3,300 for a small system. But within the context of this model, we drew the line at 1 million gallons a day for a small system. Here is the O&M cost curve. So the annual O&M costs in dollars on the y-axis. The previous slide was design flow. And so this is average flow, which is typically 3 to 4 times lower than design flow. That's why the red is going into the chart a little bit more. And so that's, again, the 3 different small, medium, and large systems accounted for in this model. So low flow conditions. So what are the issues that that are important in terms of small systems that don't really come into play with, or are at least different from large systems? And I wanted to concentrate on this because this is a small system webinar. So the first is that construction issues. So the buildings can sometimes be prefabricated buildings for small systems. So if you're under, say, 500 square feet, you can use a prefab building for a small system, and that wouldn't apply in the costing of a large system too much. Now, I should say that you can use it for small systems unless you're using something like chlorine, and then you won't be able to use a prefab building for a chlorine application. Secondly, residual handling flexibility in small, very, very small systems. You sometimes have the option of using an in-ground septic tank or septic system for disposing your residuals. And this comes into play with technologies like adsorptive media or ion exchange resins. The reduced spacing between vessels. Small systems will, their skids can be packed in closer because they're built as skids and as units, and so you don't, instead of service space of being 1 diameter of your column between vessels or equipment, instead you can pack them in a little tighter at 1/2 diameter for small systems. And this reduces all the other costs in terms of things like interconnecting piping, how much building structures you need, O&M costs, certain indirect costs are all come along for the ride because you can pack everything in a little tighter. And the next thing is smaller or no redundant vessels. Small systems generally don't need redundant vessels. If they're working with 2 columns, usually you can reduce the flow rate in a small system because demand's less, and you can operate with 1 column if you're backwashing the other. And frankly, in very small systems that have 1 column, oftentimes it's not operated 24/7. So at the times where it's not operating, you can use that time to backwash the column. So sometimes you get some efficiencies with small systems using and avoiding redundant vessels. Also, the vessels can be smaller. An example of that is in a fluidized bed system. You can use, in small systems, it's generally applicable to using freeboard of 4 feet instead of 7 feet that you would use in a large system. Reduced instrumentation. The instrumentation for small systems is often limited, and it's typically controlled by a interface unit that's attached to the skid itself, so you don't need multiple PLCs or programmable logic controllers, computer workstations, printers, and a lot of things such as that. You don't need an office or a room for the operators to sit to monitor the system, and so you can avoid some of those instrumentation costs. No booster pumps. Oftentimes some systems like GAC systems don't have limited head loss, and in a small system you wouldn't need a booster pump for those applications. Similar with backwash pumps, small systems typically use existing pumps and do not require separate backwashing pumps for backwash. Some things as almost very simple as reduced concrete pad thickness. For skid-mounted systems, you can get away with 6 inches of concrete instead of 12 for a large system that has much heavier weights. And reduced indirect costs. So skid-mounted systems require less design because they're already designed, and it's very easy to install. So you have limited and reduced indirect costs, such as you have lower mobilization, demobilization costs. You have lower construction management costs because the setup is very easy. You generally have no architectural fees. The setup is so short that you generally don't have financing costs, and oftentimes you don't have any standby power for small systems just because, again, if you don't need to operate 24/7, you can deal with some power outages from time to time. So also, there are other things that come into play with small systems, as simple as you need usually less energy for lighting and ventilation. If operators aren't present, you don't need to have the lights on. So a little bit of where the models are. Here are the models that are finished, the entire list. The ones in bold can be found on this website. Again, it's a little bit complex, and I apologize for that. But if you search Google engines for EPA space WBS, you'll find it in the top 5. And also, I'd be proud to admit that if you search for those search words in the EPA EPA website, epa.gov, it will pop up in the top 10 also. Interestingly enough, I'll just throw this out, for Bing and Yahoo, I did not see it in the top 10. So go to the EPA page on this one would be a good one. So we currently only have 3. There's actually a 4th that's available, and that's available at a different site within the EPA's webpage at this address, and a search engine that will work for all, search engines is EPA Small System Compliance Help. So if you type that into a search engine, this will pop up in the top 10 for the point of use, point of entry cost models. Here are the models that are less finished. We think we can get all the other models that aren't on the web within the next year onto the web because we have to do a lot of QA, QC, so it'll take a little bit of time. These are the models that are behind that in the next wave of models. So I wouldn't expect them in the next year, but in years to follow, we hope to bring these models up to speed for the EPA. A little bit about the integration. I think I've touched on it, but a little bit more in terms of how it fits in with the regulation. We can identify feasible treatment levels, which allows us, and we can also identify best available treatment technologies, or BAT. For very small systems, EPA has to identify small system compliance technologies, or SSCTs, and we generally have to do that for 3 different size small systems. So 25 to 500 people, 501 to 3,300, and then 3,301 to 10,000 people. And so that's why even the small systems category is broken up into multiple areas. And we need to identify essentially the best available technology for those size systems within EPA. And that's usually attached to some affordability concept with regard to household income of whether or not a system is affordable or not. And that's what designates SSCT. We can also use the 4th bullet to estimate costs for the cost-benefit analysis that EPA does with every regulation. So do the costs outweigh do the benefits, outweigh the costs for a regulation. And finally, we can estimate system-level cost to evaluate household impacts and looking at a national scale of how that would impact the country. So we're down to this is the schematic of the same thing. So before we used to do research into stuff going into the treatability database, which gives us BAT. We do research into the plugins of the cost model, which gives us the rest that I just explained. After integration, we expect the research just to be done into the treatability database, which will then feed the cost models, which will calculate everything summarily. So we believe that this will be a much more transparent way for people to understand what EPA is doing in terms of regulation. Also, I think it will make it much easier for a utility or a university who wants to do a design project or whatnot to be able to use both tools and be able to learn something about their system or a certain design. So the benefits are, I think I just explained them, so we're looking to expand the database both in terms of new contaminants and the fields that we need to do to get them to talk to each other. We have pilot tested that with a number of different contaminants such as cis-1,2-dichloroethylene, 1,2,3-trichloropropane. We've added fields to the treatability database that's going to help us translate them to the cost models, and we've added even studies for various components, including perchlorate. Now, upon looking at this list of contaminants, I've mentioned that we use this to, with the regulatory approach that EPA does. Please do not read into this that EPA will regulate any of these contaminants. These contaminants were chosen for many and various reasons, oftentimes just based on what data we had available, what current issue that we wanted to look at, and so it wasn't based at all on what compound would be regulated. So I just want to make that very, very clear. This is a repeat slide, so it's just the same. So we need to merge these two things together, the treatability database and the cost models, and there are various benefits to this in terms of simplicity and transparency. And also this last bullet I wanted to touch on is enhancing university interactions, both with supplementing the data and using the treatability data. So hats off to the University of Washington. Michael Dodd and Gregory Korshin had some classes where their students who are listed here did literature searches for various contaminants and treatments, and they vetted that through the University of Washington, handed it off to us, and we've been using that to update the treatability database. So our hats off to these students, and a job well done and very impressive indeed, and our hats off to the professors, Dr. Dodd and Korshin. So with that, Rajiv Kara's email address and mine are listed here if you have any questions, and I will hand it back off. I believe David's speaking next, and we'll have questions after that. So thank you very much.
Okay, thanks, Tom. This is Michelle quickly. I just want to remind everyone, in case you have to get off the line prior to the Q&A session, you will receive these presentations via email, which will have all of the links that you need to these tools and also contact information for David and Tom. And also, if I could remind everyone, if you have more than one person in the room with you, if you could type that number in the questions box for us, it's very helpful for our outreach. And also, if you do have a question at any point, there is the question box. You can ask a question anytime for the Q&A session at 3. And with that, I don't want to take any more time, so I'll turn that over to David.
Okay, thank you. So today I'm going to go over a couple web-based applications I've developed that deal with chloramine chemistry, and hopefully after this portion of the webinar you'll know a couple of things, and that's these applications exist, where you can find them, and how you might be able to use them. That's kind of, if you can walk away with that, I'd be pretty happy. So I just want to start off, when we're talking about chloramine, just to put everybody on the ground footing here, is that chloramines are the second most used secondary disinfectant in the United States behind free chlorine. We're typically using chloramines because they form lesser concentrations of regulated disinfection byproducts, and they're simply formed when you add free ammonia and free chlorine together. And when you do that, you can form 3 inorganic chloramine species shown here, mono, di, or trichloramine. In drinking water, we try to form monochloramine, and we control things to do that because they're not as odorous as di or trichloramine. And just a reminder as I go through this, total chlorine then is the sum of free chlorine and any chloramines in the water, but when we're talking about chloramine systems, we're pretty much talking about just chloramines. Those free chlorines can be very low. So when I think about chloramine chemistry, there's a couple areas I think about, and that's things that are going to happen no matter what happens. So when you add free chlorine and free ammonia to water, and nothing else is in the water, they're going to react, they're going to form chloramines, and then they're going to go away. So I refer to these as the formation and decay reactions, and these are going to happen no matter what else is going on. And they're controlled by some basic ideas, and that is how much chlorine and how much ammonia you add to the water. And we typically represent this as the chlorine to ammonia nitrogen mass ratio, which I'm showing here. And we typically shoot in drinking water for a less than 5-to-1 ratio to form primarily monochloramine. So just to give you an idea how what this represents, if I add 2 milligrams per liter of free chlorine to the water, half a milligram per liter of free ammonia, that's a 4-to-1 ratio. Another major factor in how fast chloramines form and decay is pH. And in drinking water, we're typically talking in the range of 7 to 9. Beyond these two things, there's a couple other items that are also very important, and that is how well the chemicals are mixed when they're added to the water. What you don't want is localized concentrations of chemicals, as that's going to not do you any benefit. It's going to cause you to have concentration gradients that can affect and also affect the pH, so you can form things you don't want to form. And also temperature is going to impact things. We're talking about a reaction here. As things get warmer, things tend to happen a little bit faster. So these are kind of the major controlling things when we talk about just having free ammonia and free chlorine in the water. Beyond this, there's reactions which I'll just lump into a demand category, and these will happen if they're present in the water. So these are things that are going to be source water specific. Everybody's pretty much going to have natural organic matter, so that's going to impact things. Chloramines can react with metal pipe surfaces and nitrite and bacterial cells. And the important thing about the demand reactions is they do kind of two things. One, they're going to reduce the amount of chloramines that initially form, so they're going to reduce what you're trying to reach if you're trying to have a residual. And two, they're going to have to make the chloramines go away faster. So that's kind of how I lump demand reactions. And then when we're talking about chloramines, a lot of times you'll hear us talk about using chloramines, you have a risk of nitrification happening. Well, nitrification is the biological oxidation of ammonia. We're adding ammonia to feed chloramine, to make chloramines. So there are bacteria out there that'll eat the ammonia that's in the water, essentially. And that turns up as demand reactions in terms of those bacteria produce nitrite and they also produce cells. So that just gives you an idea of the major factors when we're talking about chloramine chemistry. And when I give presentations, typically in the past on chloramine chemistry, I'll throw up graphs like this, where I just kind of highlight those major parameters that impact formation and decay. And here I'm just showing that, hey, as you increase the chlorine to nitrogen ratio, or if you increase the amount of free chlorine you're adding to the amount of free ammonia, you're going to decrease the stability of the chloramines that you form. And likewise, I can create a graph like this by doing some simulations and create one that just shows you that, hey, chloramines stick around a lot longer when the pH is higher. And when I give these presentations, I'll say, you know, I've implemented a model in a modeling software such as AquaSim, and that these are known reactions. You could go out and implement this reaction scheme. But the reality is that not many people are going to do that. And so some of the web applications today will help alleviate that problem. And briefly I want to back up here and talk about the underlying model and what I use to generate the simulations. Formation and decay is pretty well described by a model that's been around for about 30 years in terms of unified model. This was developed basically at the University of Iowa. So this describes kind of what happens when you add ammonia, free chlorine in the water. They react, they form chloramines, and then they go away. And this is kind of the base of all the models I'm going to talk about today. And also one of the models I've also added an example, what I call example demand reaction, just to show you what happens when there are things in the water that can also demand chloramines. And the one I'm implementing is one for organic matter, since that's going to be something that most waters are going to have in common. Now the organic matter reaction is going to be very site-specific, so they're just kind of an example demand reaction in these applications. So getting on to why I wanted to create these applications, I wanted interactive applications because when I give presentations, I simulate my chosen conditions, but I wanted anyone to be able to simulate their conditions, and it gives them a way to look at, so what happens when I change chlorine to nitrogen ratio, or what happens when I change pH, so I get an idea of the impact of my changes. And it also gives you an idea to ask questions about what happens when you're outside of normal ranges that we typically operate in. And also, ultimately, what these models allow you to do is to get an idea of your baseline chloramine stability in a system. So formation and decay represents kind of the best case scenario. So what is the maximum stability I can get for my chloramines? And that's what these models allow you to do. Also, I wanted these to be free and available on the web. A couple reasons there. I wanted them to be freely accessible. want them to be easily expanded because if they're on the web, I can just update a server and then everybody has them live. So everybody's using the newest version. There's not a bunch of different versions running around. And then finally, the end users of these applications, I kind of view as anybody who wants to understand or use forming chemistry. And the big requirement here is that you don't really need any software or pre-modeling expertise to get going on this. You can just kind of run the applications. So to program these applications, I used a freeware called R. I don't know if everybody's familiar with that, but it's just a computing and graphics software that's available at the link I showed here. Basically, I started using R when I got frustrated with Excel and its capabilities, and R gives you some enhanced capabilities. And the thing that allowed them to do the modeling I'm talking about today is that in addition to the base package, there's these what are called user-created packages that you can download, which allow you to do other capabilities with R. And the reaction scheme solves as an ordinary differential equation, so it was important to have a solver, so there's a package for that. And the other thing that made it accessible for getting it on the web was there's now a package called Shiny, which allows you to essentially slap on a web-based interface on top of R. I don't know anything about programming web pages, but I know R, and just by knowing R and using the Shiny package, I was able to create some web pages and graphical user interfaces for the web application. And so the first application I'm going to talk about today is a chlorine chemistry application. And this is basically just to simulate the formation and decay of chlorines and also gives you that example demand reaction. It can be found at the link shown here. There's some major assumptions with this model I just want to be everybody aware of. It's assumed to be batch or ideal plug flow, so either like a reaction is happening in a beaker or a slug of water moving on an infinitely long pipe. And the time then of all these simulations is an approximation to water age or pipe flow. All the chemistry here assumes ideal chemical mixing. As I mentioned, mixing is important, and so we'll make it simple. We're assuming ideal chemical mixing. We're assuming only bulk water reactions, so no pipe wall reactions, and there's no additional demand reactions besides this organic matter demand reaction that I mentioned previously. And some of the features of what I call features of this is that it allows you to select your own inputs. So one of my goals is let you select your conditions or your water conditions. It allows you to run two side-by-side simulations so you can view it how changing one parameter changes what's going to happen. Programmed in what I call 3 chemical addition scenarios that I'll go to in a little bit more detail in a bit. And ultimately, you can download the simulation data to an Excel file, for instance, to use on your own if you have a use for it. So if I'm not as trusting as Tom was, I'm going to actually just use my screenshots. So if you stretch out the application, this is kind of a map of it. I know it's not readable, but I just want to highlight that there's kind of 4 major areas of the app. There's a header area, which gives you some just general information. I'm going to go into these in a little more detail in a second. And then there's an area where you can input all your conditions that you want to run. There's an area then where you can select how you want your plots to look, and it has an initial conditions table that's going to kind of spit back out what conditions you ran to simulations. And then finally, there's an area where you can look at your plots. I have a couple pre-programmed plots to look at the data. And also 2 simulations side by side. So the header area just gives you kind of general information, version number, what this application does. I want to highlight one thing here is that there are a couple hyperlinks, which I'm blowing up here. These are the hyperlinks to the source articles that the models came from. So if you're interested in going back and digging a little deeper, you can click on the hyperlink. It should pop open the journal article if you have access to it. If you don't, you'll be able to figure out the reference to get it from the library or something like that if you need it. The next area then is the inputs area. So this is where you input all your initial conditions. And I'm just going to kind of bounce through a couple areas here. There's a couple buttons at the top. The top one here is the way to easily copy inputs from simulation to simulation. So this is helpful if you want to compare 2 simulations by changing one parameter. You input all your conditions on simulation A, for instance, copy them over to B, and just change your one parameter over in B. And then there's a button that you actually hit to run the simulations themselves. The next area is where you select your chemical addition scenarios. So this just effectively selects how you're adding free ammonia and free chlorine to the water. And as I mentioned, I have 3 types of simulations scenarios you can select, and by selecting this, you'll change how you enter free chlorine and free ammonia. So this one I have simultaneous addition selected, and that gives me 3 options to enter in my free chlorine. Either I can enter a known concentration, or there's some ability to enter in if you're feeding gas or liquid. And then free ammonia gets you kind of 4 options, either known concentration, chlorine nitrogen mass ratio, or gas and liquid. So that's just kind of how you'll enter in the free chlorine and free ammonia. The next area, you enter in your water quality. So these are the things, it's just pH, alkalinity, temperature. And these are just held constant during the simulation, but you can easily move the sliders to select your condition that you want. And then the next area is where we have the ability to turn on, I would say, the organic matter demand reaction. Initially, it's set to 0 as the TOC concentration, so that just effectively turns this reaction off. If you want to turn it on, you just put in your TOC concentration and then select a fast or slow reactive fraction. I don't have time to go into detail what this means right now, but the Dewar source article up in the header will explain what these mean in detail if you want to reference those in the future. And then finally, it's an area where you select the time scale for the simulations. Chloramine reactions kind of happen on 2 time scales. The formation reactions happen on the order of a minute, and the decay reactions happen on the order of hours and days. So depending on what you want to focus in on, you can select different time scales to run the simulations. And what this is going to ultimately determine is how long the simulation runs for, and the scales on the plots that are generated in the application. And finally, the button at the bottom is where you would download. Hit that and you'll download an Excel file of all the data for the underlying simulations to use offline. One other thing I want to talk about here in the application is the idea of tooltips. So I'll blow up this top area here. Any box that requires an input from the user in this app is going to have a pop-up box like this. It's going to tell you what it's looking for or what I want from you in terms of an input. And right here we're talking about the 3 different chemical addition scenarios. And I just kind of want to go into what each of those mean in a little bit more detail to give you an idea of what I'm looking for here. So with simultaneous addition, it's pretty much what it says. You're adding free chlorine and free ammonia together simultaneously. So you can have a system where you are adding free chlorine. It's well mixed to the water. We're assuming no demand of that free chlorine before the free ammonia is added, and that's well mixed. So the simulation starts from this condition of having this well mixed solution of free chlorine and free ammonia. And so it doesn't matter what's added first. It just this is where it's starting from. So this would kind of simulate forming chloramines in a treatment plant, for instance. The next would be preformed chloramines, and as it says, we're just talking about a solution here that you have monochloramine, dichloramine, free ammonia. You've already formed your chloramines, and you want to see how long they're going to stick around. I just want to mention at the top here, I'm just representing kind of pipe flow. I'd like to mention ideal pipe flow, and the bottom is a beaker, essentially in a lab, for instance. So what this is going to be, it's going to be akin to taking, say, a sample of water leaving a chloramine treatment plant and just holding it and then looking at how long the chloramines stick around with time. Or you could take a sample out in the distribution system and do the same thing. But any case where you have preformed chloramines, essentially no free chlorine initially. And then there's situations with chloramine systems where maybe the distribution system residual has decreased, or you have a little bit too much free ammonia leaving your treatment plant and you want to boost your chlorinate, which means we're starting with a mixture of chloramines, has some ammonia, monochloramine, maybe some dichloramine. We have one that has too much free ammonia though, so we want to add a little free chlorine to recombine the free ammonia and the chloramine. So this would be if you're boosting chlorine out in the distribution system, or if you're mixing a water that is free chlorine with a chloramine water. This is what a simulation, this is trying to simulate. So the recombination of the free chlorine back into chloramines and then its decay. And then the next area is where we mentioned talking about choosing plot preferences and the initial conditions table. So here you can quickly check on the boxes you want of the chemicals you want to show on the plots that are generated. And then also it spits out again the initial conditions that you selected for your simulation. So this chart will tell you what are the conditions that were used to generate the plots at the bottom of the application. So in terms of the plots themselves, there are 3 types of plots that I have standard in here. One where we look at all the individual chemicals versus time on their own separate plots. The second one is where you just throw all the chemicals together on one plot. And the third is looking specifically at chlorine to nitrogen ratios over time. So just an example of the individual chemical plots here. I'm showing total chlorine and monochloramine versus time. Then the composite plot is just what it says. So I'm blow up this plot here, and it just shows you all the chemicals at once over time. So it shows you the formation and decay of chloramines. And here I believe we're talking pH 7, about a 4.75 to 1 chlorine to nitrogen ratio. And what I want to point out here is something interesting that you'll see with these simulations in terms of dichloramine concentration. As I mentioned, chloramines form rather quickly, so that's where you see these spikes on these concentrations. So you have a mono, a di, and a free ammonia concentration. What's interesting about when you get around below pH 7.5 or so and you're operating at close to a 5:1 ratio is that your dichloramine peak formation isn't until about a day out. So the dichlorine leaves the plant will actually be lower than what you may measure out in your system. And this is also happening at the same time total chlorine is going down. I had a utility contact me where this is actually going on. They were seeing their total chlorine go down with their dichlorine going up in their system, and they were kind of operating under these conditions. And this simulation was able to help kind of tease out what was going on there. And then finally, there's these chlorine and nitrogen ratios, and there's kind of two plots here representing chlorine to ammonia nitrogen in the top black line, and then the magenta line is on a chlorine to ammonia basis. So just two different units in looking at the ratios over time. Just a couple other things about the model, just kind of to prove that it works. This is data from the source articles that the model was programmed from, just showing you that the implemented model represents the experimental data really well. Another thing, as I mentioned before, that I typically program in a different language, AquaSim, and this is just a simulation run in AquaSim and the web app, just to show you that numerically the two applications are running exactly the same. And then finally, we'll talk about an example application with this application. So here we have two water systems where Matt Alexander from the Office of Water went. He pulled water, finished water, leaving the plant. And you can see the chloramine decay over time here. And the thing the application can do is kind of let you judge, is this a bad decay, a fast decay, a slow decay, without having a way to judge it. You don't know how reactive the water is. So for system one, we simulated the data, and the model simulates it pretty much right on, which tells us that that water leaving the plant in and of itself is not that reactive. It's kind of decaying as it would as if nothing else was in the water. But system two, you see something quite different. You see a much more rapid decay than what we predicted from the simulation, and it ends up to be about a 0.7 change. So if you just kind of shift that line down, you see that there's something going on in the first, say, 8 to 10 hours that's really happening fast, which is probably the organic matter that's left in the water most likely. But it just gives you a baseline here, which is what I think the applications are nice, is they give you a baseline of what should be your best chloramine stability that you can actually achieve. The second application I'm going to talk about deals with breakpoint curves. Those unfamiliar with the breakpoint curve, it's kind of an easy way to look at how chlorine and nitrogen mass ratio impacts chloramine concentrations and how much chlorine it takes to take out ammonia in water. So what we have here is just a typical breakpoint curve. On the y-axis is going to be total chlorine and free ammonia. On the x-axis is going to be increasing chlorine and nitrogen mass ratio. So for a given free ammonia concentration, as you move increasing on the x-axis, it just means you're adding more free chlorine to the water. So we start out with some free ammonia, no chlorine added. And if we keep on adding free chlorine to the water up until about a 5-to-1 ratio, what we're going to end up doing is combining the free ammonia in the total chlorine. And this will happen up to the stoichiometric ratio, about how much free chlorine you need to add to combine it all into chloramine. And then if you keep on adding free chlorine, you're going to actually start to destroy your chloramine residual up until the point where it's the break point where you've oxidized all the nitrogen out, essentially. And then if you keep on adding chlorine, you'll have a free chlorine residual. Well, this is kind of a typical breakpoint curve. There's assumptions, though, that are underlying a breakpoint curve. A breakpoint curve is for a given reaction time. This is not a static thing. It's changing through time. And it's also dependent on the conditions, as pH has a big impact on what these look like. And so I wanted to create an application that would simulate breakpoint curves. And again, in drinking water, we're usually less than 5-to-1. So the breakpoint curve application is located at this link. And some of the uses I see for this is, one, it gives you a first cut of how much chlorine it's going to add, it's going to take to remove any influent ammonia if you are breakpointing, and also the time involved in that, because that's something that the breakpoint curves usually don't address. Also, it gives you an idea of if you're operating close to 5-to-1, what does that mean in terms of forming other chloramine species, and it depends on pH. And then finally, some assumptions and features of this. It's similar to the chloramine chemistry app in terms of what it does, but this does not have any demand reactions in it. So again, it's kind of like a perfect breakpoint curve. So what this does is you input your ammonia concentration, and then the simulation is going to go through and run all these different chlorine and nitrogen ratios for you. So you end up doing about 76 simulations, and it runs them for a period of 4 hours. And then what you're able to do is to be able to plot the breakpoint curve for a specific reaction time, and you can also animate it. So the layout again, if I've road mapped it out, it has kind of the same 4 general areas, and you can run side-by-side simulations. Same header area, kind of. There's hyperlinks to the source articles. Same kind of buttons to copy from simulation to simulation and to run the simulation. And the initial conditions area here is a lot simpler. It's just looking for the ammonia concentration that's there initially, pH, alkalinity, and temperature. And again, you can download the simulation data by clicking the button. It'll be a much larger file this time. So here is where we're generating the output plots. Again, you can select which chemicals show in your breakpoint curve. The new thing here is each breakpoint curve is set to a reaction time. So you select the reaction time you want to show in the plot down there, and there's a button in the lower right here. If you hit it, it'll animate it and step through every 5 minutes. So then you actually have your breakpoint curve here, which is showing all the chemicals through time. Again, concentrations here on the left, on the y-axis, and then chlorine nitrogen mass ratio on the x-axis, and all the different chemical concentrations. And here's the 15-minute reaction time. So the final thing I want to do is kind of walk through an animation just for 2 different conditions. Everything being the same except for the left is pH 7, the right is pH 9, and 1 milligram per liter of free ammonia to start. And at time 0, things are pretty boring. Nothing's happened yet. But there's a big difference even just going to 15 minutes. At 15 minutes, we start to see, I'm going to focus in on the black lines here on both of these. The breakpoint curve kind of is resembling what I said was a theoretical one before, where you see the hump and the decrease and then an increase after some point. Where at pH 9, things are happening a lot slower. And also at pH 7, you see you're forming some dichloramine, where at pH 9, you're really not predicting any dichloramine formation because it just doesn't want to stick around at pH 9. So after 30 minutes, again, the pH 7 one is pretty much done. The pH 9 one is slowly occurring. Why I want to point this out too is I had actually at the conference that I just arrived back from, I was talking to a utility, and this is kind of, they were a pH 9 system, had some ammonia in their water, and they were operating as a free chlorine system, but they were operating at a chlorine to nitrogen ratio in this range here. Why they're remaining a free chlorine system is because under these conditions you can maintain both a free chlorine and a monochromium residual, and they were just kind of by happenstance being able to maintain a free chlorine residual because of their pH and the short reaction times that are going on in the plant. As we continue on, it's 60 minutes. You can see, again, pH 9 is starting to finally look like a breakpoint curve over there. And then it continues on for 4 hours. They're kind of both complete. So at pH 7, what we see is that things happen a lot faster. And then when you're done with the breakpoint reactions, before the breakpoint, you have both mono and dichloramine present. Around the breakpoint, again, we've taken out most of the chlorine residuals, so nothing's really there. And past it, you see some free and trichloramine. At pH 9, it's a lot slower. Before the breakpoint, it's pretty much only monochloramine. Around it, you see a little mono and free, and then post it, it's pretty much free only. And so that quickly went through a couple web-based applications. Again, the first one is really just to simulate formation and decay of chloramines, plus to provide an example demand reaction to show you what happens if there's things else in the water that are going to take out your chloramine. And the second one was just to be able to generate breakpoint curves for a given condition and reaction time, essentially. These, again, are free and online, and they're available for use. And I personally view them as learning and application tools. Learning tools first, and that it gives you a way to easily play with chloramine chemistry and get a feel for the system, for lack of a better word. But there are also, as I've hopefully pointed out, there are applications to these where they can give you a baseline to interpret what's going on and to look at how changes might impact your chloramine stability or what chloramines you might form. And then there's a lot of things that can be added to these in the future, and I'm just kind of listing them here for right now. But there's a lot of stuff that could be added in the future. And I want to acknowledge Matt Alexander, Alicia Deal, and Jerry Spital as they helped me going through this app. Matt collecting some data, Alicia and Jerry providing some feedback on functionality and capabilities. And again, some links where the web-based applications are located, some of the model references for the established models I used in the applications, and just some general software links if you're interested in R and Shiny, and maybe you have some projects that you think could adapt to this web-based framework. And that's all I have.
Okay, thanks, David. Okay, thanks everyone for joining us today. If you have to leave, just a reminder that you will receive this presentation here this week. And also, if you have people in the room with you who need certificates, just go ahead and email those names to us or type them in the question box. And before we begin, I also want to remind everyone that next month we do have one more webinar for the 2015 series, and it will be December 15th on reduction of lead in drinking water. That invite will be going out shortly. And also, I do want to let you know, which we will talk about more next month, but many of you may not be able to attend next month, but We will continue. We are planning on continuing the webinar series in 2015 or 16, excuse me, and we will talk about that more and send out more information to all of you when we have that ready. So with that, I'm going to go ahead and start. And David, I will go ahead and start with you, if that's okay, and ask you a couple questions here. Okay, does the chloramine chemistry also address ozone quenching?
Not in these applications.
Okay. And how can the chloramine model be used for a consecutive system receiving chloraminated water?
So that would be kind of you would simulate that as a preformed chloramine, I would say, and then if you were, say, boosting the residual, you could account for that depending on how you're boosting it. If you're adding free chlorine to combine some of the free ammonia, that would be the booster chlorination scenario. So it would be you poise the model under the simultaneous conditions of what the quality that you're getting in terms of ammonia, pH, dye, monochloramine, and then from that point entering your system, you can get a rough estimate of stability from that point on.
Okay, thanks, David. I'm going to go ahead and switch to Tom. That's now about the cost models here. And okay, Tom, are you on the line? Can we hear you?
Yes, I think so.
Okay. Okay, so your first question, do the cost models utilize present value equations, and if so, how do you estimate useful life for each individual unit operation?
Okay, excellent question. So the model annualizes capital costs. So it estimates the useful life for each individual treatment component, because that's important, because pipes will last longer than mechanical parts and things like that. And then it uses a weighted average to estimate the useful life for the whole treatment system. And so we get that information from vendor input and also from state government data. So yes, the answer is yes.
Okay, thanks, Tom. Okay, Tom, I'm just going to go ahead and ask you. We have, and by the way, I did forget to mention, we will try to get through all of the questions today, but if not, Tom and David's contact information, again, will be available, so you could always email them with a question as well. Okay, Tom, are there plans to add Legionella to the treatability database in the near future?
No, there are no plans right now to add Legionella. Part of the issue is that Legionella is a very premise plumbing issue and is only part of the equation, handling the conditions within the pipe. It's all related to treatment, but there are other issues, and so it was a little interesting because it came up, and we kind of looked at it and said not necessarily the case. So that being said, I think that the Office of Water came out and with a document in terms of Legionella control. And that document was released October 21st, and it was presented at a public meeting on November 9th. And a lot of the information on the treatment and control of Legionella are in that document. So upon saying that, it would be a fairly easy thing for us to do to create a page on Legionella. So it's interesting. We might attempt to do so in the near future.
Okay, Tom, I'm going to ask you another question here, and then I'll move to David for a question. Do labor costs adjust for locale?
Okay, the answer to that is no. The labor is calculated out in a national average wage rate. This is something that could change. You could easily adjust that. Well, I take that back. You can't easily adjust it. It would take a little bit of Excel savvy to adjust it. So the answer to the question is no, and it's a little change that.
Okay, thanks, Tom. David, I'm going to go ahead and give you a question here. How can the chloramine model be used for consecutive system receiving chloraminated water?
Yeah, that one.
Sorry, I thought it sounded familiar. Okay, Actually, I'm going to go ahead and go back to Tom here,
Okay.
David, for a second. Okay, Tom, is the work, whoops, I just jumped around here, excuse me. Is the work breakdown structure spreadsheet available on the website or available somewhere else?
Is the spreadsheet available on the website? Yes, the cost model is available on the website. I gave you 2 links. The key is to go to a search engine like Google, and you can Google EPA space WBS, and that will take you to 3 of the cost models for GAC, bubble aeration, and packed tower aeration. And if you Google or search for EPA small system compliance help, you'll be able to find, it's somewhat halfway down the page, but you'll be able to find the cost model for point of use, point of entry devices.
Okay, thanks, Tom.
And
okay,
I'm sorry, those will be on the slides once they're put out.
Right, yeah. And the links to all of the tools we have here will be on the slides when you get them. Okay, Tom, another question. Do the cost models take into account the potential expensive disposal of waste stream? For example, radionuclide disposal.
Absolutely. So waste streams and residual control are very well accounted for in the cost models. There are some assumptions that are taken, but those assumptions are easily changed within the cost model. Definitely all aspects of residual control, whether it be backwash water or spent GAC or spent ion exchange resin, and you generally get a choice of maybe 8 or so different options of what you would do with that waste. And it also is dependent on size and whether or not you have tanks to hold the backwash and issues like that. So it's definitely included in the model.
Okay, Tom, another question about the cost model. Does the treatment cost model account for cost differences caused by geography location?
Okay, so this is similar to the labor cost question. So this is about the unit cost. So the unit costs are a national average also. But unlike the labor costs, they're fairly easily changed by the user. So you can use a city index and use to adjust the material costs by indexing them to local prices. So in terms of the unit costs, both can be changed, but the unit costs can be changed more simply than labor costs. So the question is, it's a national average, but you can change it.
Okay. Tom, one more question here. The question is about waste streams and about wastewater treatment plants. And the question is that the database and cost models, do they work on wastewater treatment?
Okay, so contaminants for wastewater treatment systems. This model was geared toward drinking water. So it was geared toward helping the EPA along with the drinking water regulations primarily. As I said, it has multiple uses for multiple people, but it's fairly strictly a drinking water application. You could probably look at it if you're savvy enough and glean some things from it for wastewater applications, but the model's intent was with regard to drinking water.
Okay, well, actually, that is all the questions we have. Unless anyone else has any other questions they want to ask, you could type it in right now, but if not, then thank you all so much for joining us today, and thanks Tom and David. Again, a reminder that we will have our last 2015 webinar in December on the 15th, talking about reduction of lead in drinking water. And thank you all so much for joining us.